Okay, in this section we're going to be looking at 6C and 6D. So that's going to be methods of heat transfer and then also specific heat. So we're going to get started with 6C. So the first thing in 6C is that there are three fundamental methods that thermal energy can transfer from one object to another. The first of these methods is going to be conduction. Conduction. And that's going to be heat transfer um, by objects physically touching one another. So like putting your hand on a hot stove would be an example. So again, if you have objects that are physically touching each other, and then you get a heat flow between them, that would be conduction. The next method of heat transfer is going to be convection. 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 That's going to be heat transfer that involves the movement of fluids. So fluids could be liquids or gases. So an example, wait on this for a second. So an example of this would be smoke rises from a fire, or smoke from a fire rises over the cooler air around it. So again, anything where you get a movement of fluid and then you get some type of transfer of heat from one thing to another, basically, that's going to be convection. Another kind of thing to note with convection is the reason convection happens is because hotter fluids rise over colder fluids. So again, if you have hot air, that's going to tend to go hot air, that's going to tend to rise, and cool air, that's going to tend to kind of stay where it is. It's sort of, I guess you could say it's falling. So again, because of the difference in the hotter temperature between the hotter and cooler air, you're going to get a movement of fluids, and that's going to be convection. And the last method of heat transfer is going to be radiation. Radiation. So that radiation is going to be heat transfer through a vacuum or transparent medium like air. For example, the sun heats the earth through space. So you have a sun, it's really sending heat. How we get the heat is you're getting it's moving through space and then the air in the atmosphere to us. So that's radiation. Again, radiation, it doesn't necessarily need to go through something. Like convection needs to go through a fluid, conduction needs to go through a solid usually. Radiation does not. It could really go through most things. So those are the three methods of heat transfer. Are conduction. So again, two things touching, you get a movement of heat. Convection, you have moving fluids, and you get a transfer of heat. Or radiation, it's just something's radiating heat out, like from the sun, and it's going through. Basically, it could go through nothing or something transparent. Basically, that's when you'd say there's radiation. Okay, so that's pretty much it for 6C. We're going to move on to the last section, which is a little bit longer, so that would be 6D. 6D. Yep, here we go. So 6D is going to be about specific heat. So specific heat is a property of an object to resist changes in temperature. So another way you could think of that is thermal inertia. So normal inertia, if you have lots of inertia the way we normally think about it, it's hard to change an object's motion. If you have lots of specific heat, so if you have higher specific heat, that means you're going to have more heat to change your temperature. So it's basically, the resistance to changes in temperature is specific heat. So the standard unit for specific heat is a little strange. It's going to be joules divided by or per kilogram times Celsius. So that's the standard metric unit for a specific heat. It's important to note some materials have high specific heats, like plastics, plastics, water, glass, and some are going to have low specific heats. Like metal is a good one that has a low specific heat. So if you have an object, basically, I don't know, we have some metal, and then we have some water. Sure. And if you put heat into both of those, if you put the same amount of heat into metal and the water's temperature is going to rise not that much, a little bit, but the temperature is going to rise a lot. And the reasoning for that is water has kind of a high specific heat, so it's going to tend to resist the change in temperature a little bit more. Metal is a low specific heat, so you put in heat, you're going to see the temperature rise a lot more for that given amount of heat. It's important to note, though, that specific heat only says how much heat's required to change for a given change in temperature. It doesn't really say how fast heat's going to flow into that object. So again, specific heat says how much heat is required. Like, you could say, oh, there's 100 joules required to raise this water so many degrees. But it does not say how fast that's going to happen. That would involve another concept. So the amount of heat required to raise a substance a given temperature is dependent on the specific heat we've looked at, but also the object's mass. So this equation here, I guess you call it the heat equation, describes basically how much heat's required to raise something a given temperature. So let's go through each thing. So the heat is Q. That's going to have the unit joules, right? Because heat's really thermal energy. The next thing, mass, M, right? We've seen that before. That has the units kilograms. And that's how much mass the object has. And then specific heat, right? The thermal inertia, how it resists changes in how it's going to resist change in temperature based on how much energy goes into it. Then the last one, change in temperature, and that's going to have the standard unit of Celsius. Change in temperature, right? Change in anything is really the final minus the initial. So another way you could write this is delta T is equal to TF minus TI, the final temperature minus the initial. So again, if you have this equation basically says, okay, if you have an object, square, I guess, and you put, so you have an object, you know what the object's mass is, you know what its specific heat is, and you put a set amount of heat into it. This is basically going to tell you what's going to happen to the temperature, whether it's going to go up and by how much, really. So that's the point of the heat equation, is we can one of the things we can do is really predict changes in temperature based on how much energy goes into something. So that's really all the stuff. Just to quickly summarize, we get specific heat is a new idea. It's like thermal inertia. It has kind of a strange standard unit. Materials are going to have different specific heats. Specific heat really doesn't say how fast something's going to heat up, only what its change in temperature is going to be ultimately, given a fair bit of time. And we got the heat equation that's going to let us analyze heat more mathematically. Okay, now we're going to actually look at a problem. Here we go. So again, before I go through this, make sure you're attempting the problem first. So again, you're attempting the problem, you're not playing Candy Crush. Okay. we'll get started. So what we have here is you place 0.8 kilograms of water into a microwave. I guess it's assuming it's in a container of some kind. So 0.8 kilograms of water, 20 degree C into a microwave. The microwave provides a set amount of energy into the water, and it begins to boil. So two things. The first, well, I'll sketch it out actually a little bit. So we got water in a container of some kind, not clear exactly what container. So water, and then it's in a microwave, so we get some heat transfer. We call that Q. So what's the method of heat transfer causing this water to boil? What method of heat transfer? So there's three of them. If you're in a microwave, what's really happening is a microwave, it releases basically radiation. They're microwaves. So again, the microwaves are traveling inside the microwave from the emitter, and it's traveling through the air in the microwave into the water that you're looking at. So this is actually going to be a case of radiation. Radiation. So again, because it's a microwave, the microwaves basically are causing the radiation, or are causing the water to heat up. B, what's the specific heat of water? So we know we're looking ultimately for C, but we know a bunch of stuff. We know Q, we know M, and we know Q, we know M. We know the initial temperature is the 20 degrees C, and we know the final temperature. It says it's boiling, so it's 100 degrees C. So what we have is, if we're trying to tie all those together, we're going to use the heat equation, Q equals mc delta T. So we know how much energy is provided, we know the mass, we know the change in temperature, so change in temperature is really Tf minus Ti. We know both of those things. So we're looking for C, so we can find that. So we're going to plug in, basically, we're going to do 267,904 joules of energy, thermal energy going in, the mass, 0.8, looking for C, and then delta T, I'm just going to do it up here, Tf minus Ti, the final is the boiling point, so it's 100 degrees C, the initial is 20, so we're going to have a delta T of 80, really. So I'm going to plug that in. So 80 degrees C is the change in temperature. So again, we're dividing out one side by the other. We'll get C is going to equal 4,186 joules per kilogram degree Celsius, because that's the standard unit. And that's actually, if you look it up, that's the standard kind of specific heat of water. Okay, so that's about it for these two sections.